Good evening and welcome to the spring 2022 semester's first installment of the renewed Mason Vision series. Our apologies for getting started a little bit late, some technical difficulties this evening, but we're so glad you're with us for this monthly forum to showcase exemplary real-world research and scholarship that takes place on George Mason University's campus each and every day. I'm Mark Ginsberg, and I have the honor and privilege of serving as Provost and Executive Vice President at George Mason, and also have the privilege of hosting the Mason Vision series. Many of you watching tonight are outside of the Mason community, so let me just take a moment to briefly talk about George Mason University. Today, Mason is the largest public research university in the Commonwealth of Virginia, and we're one of 131 United States universities to receive the highest research designation, that is the R1 designation, from the Carnegie Classification of Institutions of Higher Education. We operate campuses here in Virginia in Fairfax and Arlington, our Science and Technology campus in Prince William County, as well as a wonderfully engaged campus outside of Seoul, South Korea, in the Songdo area of Seoul. Our student body is over 39,000 students who are from more than 130 countries and every state. And Mason was recently ranked as the most diverse university in Virginia and the 21st most diverse university in the United States by U.S. News and World Report. Well, the Mason Vision series presents an opportunity for invited members of the Mason faculty to share the frontiers of their work in an accessible style that inspires a lively discussion among our students, among our faculty and staff, and the wider reaches of our community. Under the initial leadership of our former Mason Provost, Dr. Peter Stearns, the original program began in the fall of 2011, and it featured speakers at in-person events at all three of our campuses. We resurrected the Mason Vision series about a year ago, and it has proven once again to be a wonderful opportunity for both presenting faculty and those who attend with inspiring information and opportunities for conversation. Tonight, we will hear from Hakeem Ashuwehi.
Close enough.
I'm sorry, me.
Dr.
Hakeem
O.
Alushehi. Tonight, we
go.
will hear from my distinguished colleague, who's internationally recognized as an astrophysicist, TV personality, inventor, humanitarian, and a global science education activist. Professor Alushehi is a visiting Robinson professor here at George Mason University. And he currently has over 7 US patents, 4 EU patents, over 60 scholarly publications in areas of astrophysics, optics, and detector technologies development, in nanotechnology manufacturing, in observational cosmology, and in the history of astronomy. Dr. Alushehi's current work includes investigating galactic structure and formation using time domain survey data, analyzing big data using astroinformatics and high-performance computing. His views, his professional mission, his work is to advance humanity's understanding of the universe through scientific inquiring, for passing on the detailed knowledge of this process and its results to the next generation, and to be in service to both humanity and to our country. Tonight, you'll hear from Dr. Alushehi about his research, which is focused tonight on his talk entitled Hacking the Stars. The foundation of his work is in 2 areas of astrophysics, astronomical survey science for cosmology and solar plasma physics. Hacking, by the way, references the fact that he not only utilizes observations and the theory of the sun and stars to advance knowledge of the objects under study, but also to develop new technologies and advance understanding of other systems. It's a great pleasure to introduce my colleague, my friend, Professor Hakeem Alushehi. And as he engages in his talk with us this evening, you will have questions. I'm confident that his talk will raise many questions. And you could raise your questions for conversation after his talk by submitting questions to this email address, GMUP in caps, GMUPROV@gmu.edu, or via Twitter using the hashtag Vision Series Mason with VS and M in Vision Series Mason capitalized. Again, GMU Probe, GMUP in capitals, small letters ROV@gmu.edu, or via Twitter at the hashtag Vision Series Mason. And now we again apologize for the delay in beginning this evening's program, but it's a great pleasure to introduce Hakeem Alushehi. Hakeem.
Thank you, Dr. Ginsberg, Mr. Provost. I appreciate you having me here today. Am I on the air? That's the question. I see the Vision Series slide up. Am I on now? Am I being projected? Well, I'm going to share my screen. Let's do this and switch over to my talk. All right, so let's see how this goes. Thank you all very much for joining me this evening. My talk is called Hack the Stars, or Hacking the Stars. So as Dr. Ginsberg says, I study stars for the purpose of understanding the stars, but stars also serve as an inspiration for new technologies, as well as they can serve as tools for studying other systems, the galaxy, the universe, and other galaxies. So there's another meaning when I say hack the stars. You see, my title of my recent book is My Unlikely Journey from the Street to the Stars. So sometimes we use the word stars to refer to our futures, right? It's written in the stars. Well, one of the things that brought me to Mason is the fact that we all come from various different walks of life. And here is me as a little bitty kid there in New Orleans at the age of 4. And, you know, I come from humble circumstances. Nobody in my family had acquired a high school diploma, let alone a college degree, but yet here I am. And so one of the things that drew me to Mason is that Mason serves people just like me, from communities that may not have the history of academic attainment, and people are trying to improve their lives. Now, of course, many of our students do have that, and we give them exactly everything that we have, no matter where they're from. But I can say I do hold a special place in my heart for those who are striving to better their lives. Now, what I wanted to do is share with you, for those of you who are unaware of the stuff that I do on television, I want to share a little bit of a sizzle reel from one of my previous shows, not one that I'm in today. It's no longer on, but it gives you a sense of my personality and how I do things on the air. So this is definitely a wait for it.
People in the ABAC industry told us that what we were trying to do was impossible, and it was a great feeling to prove them wrong 7 years later.
We asked Hakeem to simulate a bicycle accident.
All right, here we go. Okay, that didn't work. All right, you see, I love to have a lot of fun, whether it's communicating or whether it's actually in the lab doing science. And I started off my scientific career doing something incredibly cool, and that is studying the nearest star, our sun. And what you see here is illustrations of the way the sun looks in different wavelengths of light. But these wavelengths of light are carefully selected because what they allow us to do is image the sun at various temperatures. Now, the development of this technology, as I'll show in a minute, was the foundation of my PhD work. And what I do now is, you know, we've come a long way. I was on the team that developed these technologies and did this for the first time, but now that was, you know, back in the late 1980s. So here we are, 30 years later, more than 30 years later, and things have advanced significantly. And so what I've done is I became fascinated with the study of light. And what do I mean by that? I often tell my students, I ask them 2 questions. One question is, what is matter made of? And typically, they have the right answer. They'll say atoms. And for those who are more advanced, they'll start talking about protons, neutrons, electrons, or maybe even quarks. But for the average person, when I ask them what's matter made of, atoms is the correct answer. But when I ask my students, where does light come from, right? Most people say the sun. Some people will say energy. And I point out that, you know, energy is something that is possessed. And at night, there's light without the sun. So the simple answer to where light comes from is matter makes it. And when matter makes light, the signature of what the matter is and what the matter is doing is encoded in the light. Now, we're in an area with highly educated people, so I'm sure some of the nerds out there are thinking, hey, Dr. O, can't neutron stars and black holes create light from the fields around them sometimes? Yes, they can. But most places in the universe are nowhere near a black hole or a neutron star. So for the most part, matter makes it. Now, when I say the universe, here's what I mean. What you see here is a simulation created from real data. The data is from the Sloan Digital Sky Survey, and the Sloan Digital Sky Survey team, along with scientists from Lawrence Berkeley Lab, created this animation. And what you see here are galaxies in our universe. So when I speak of the universe, this is the scale that we're talking here. So each galaxy that you see is hundreds of billions, contains hundreds of billions of stars, and is over 100,000 light years in size. And in our visible universe, there are at least 2 trillion galaxies. What we see in this simulation is just 500,000. So when we study our nearest star, it actually allows us to understand the universe on this scale, because where is the light coming from that you see in these galaxies? All of that light is created by stars. It's the integrated light of hundreds of billions, if not trillions of stars. But when we say the universe, what picture do you have in your mind? Let me give you some numbers that will bring it down to earth for you, but also give you a more tangible idea. So one of the things that we physicists and scientists like to talk about is how big and empty space is. But you know what? We can bring that down to earth for our own bodies, right? We're all made up of matter that's contained in atoms, and the actual meat, all of the mass, is in the nucleus of those atoms. And it turns out that the atom itself is 100,000 times bigger than the nucleus. So that means that an atom is mostly empty space. And when you look at something like our cells, solid matter, the mass, those nuclei are a few 100,000 times their own size apart from each other. So even you are mostly empty space. And when you look at these galaxies here, they look almost solid. But if you were to look at them in detail, you'll see that stars are only a couple light seconds to a few light seconds across, but they are light years apart, which means that stars are a few million times their own size apart from each other. Now let's take that up to the scale of galaxies like you see here. If the nuclei in your body are a few 100,000 times their own size apart, the stars in galaxies a few tens of millions of times their own size apart, what would you guess the number is for galaxies? If you're like me, you would extrapolate it to an even bigger number. But it turns out that's not the case at all. Galaxies are on average about 10 to 1,000 times their own size apart from each other. Like the nearest large galaxy to us, the Andromeda Galaxy, is only 20 Milky Ways away. So guess what else is about 1,000 times their own size apart from each other? The air molecules in air at standard temperature and pressure. So the best example for galaxies in the universe is air in the room you're in right now. Kind of mind-blowing, isn't it? But that is what our universe is. And the whole thing is expanding. So how do we come to understand it? Well, one step at a time, just like everything else. So let's start out with where I started my research, which is observing the sun. I've still done this recently. I last published, now I have to let you know, I was administrator at NASA before coming to Mason. So at that time, I didn't do any research or much research. So the last papers I published were in 2017 on this topic, but we're gearing back up right now. And here we go. So here is the sun in soft X-rays. And the normal bright surface of the sun that you see is black in this image. The visible light is blocked out, and the X-ray light, which is 1 billion times weaker, is now visible, and we're able to image it. Now, my early work was in developing the technology that allows us to do this. And here were our early images from the early 1990s, right? Now we get this stuff every day, so it's, we take it for granted. But back then, it was very new, and so there were a lot of questions about the nature of the sun's atmosphere. We completely understood stars from their core to their surface, but once we got to the surface, things fell apart because no one predicted that these magnetic fields would rise to the surface and they would interact in various ways that would heat the plasmas on the surface of the sun to 1,000 times hotter than the plasmas below. So whereas the surface of the sun is thousands of degrees Kelvin, 5,800 degrees Kelvin roughly, the plasmas you see in these images are at millions of degrees. So that is known as the coronal heating problem. How can you have a 5,800 degree surface indefinitely maintaining a 1,000,000 degree atmosphere? Now, the other problem is what is known as the solar wind. Gravity at the surface of the earth is gravity at the surface of the sun is 30 times stronger than gravity at the surface of the earth. But the earth's atmosphere does not stream away into outer space, but the sun's does. What is powering that acceleration? How could so much energy go into this plasma that it could actually fly away from a large mass concentration like the sun? Those are the two interesting problems. So here's an example of the new technology. Basically, and when I say new as of last century, the end of last century, if you take this equation, forget about the sine theta, because theta equals 1. You coat the mirrors of your telescope with layers of molybdenum and silicon. Light comes in, and just like when you see a rainbow, when you see oil on water, that is known as diffraction. The equation you see at the top there is known as the Bragg diffraction condition. And so what this tells you is that by making these layer thicknesses D, you control what wavelength lambda is reflected. And that way, we can choose what wavelength of light we reflect. And based on the processes in the sun's plasma, we can say, hey, here's a wavelength of light that is created at 900,000 degrees. Here's one at 1,000,000 degrees. Here's one at 1.5 million degrees. Here's one at 2 million degrees. So we tune these telescopes to specific wavelengths that allow us to take photographs of the sun at various temperatures. Then we can create models of the plasmas. And in these models, we can use each of those, the emission and the sizes at various temperatures, to constrain those set of models that fit what we see. And here is a photograph of my first rocket flight. And there is my late PhD advisor, the late great Dr. Arthur Bertram Cuthbert Walker II. He's one of the first 3 African Americans to actually get a astronomy degree in astrophysics in America. And he was the first person, period, to do X-ray astronomy of the sun. And so I became his protege. The gentleman in the white blazer there, that's Dr. Richard Hoover. So for those of you who watch Ancient Aliens, he's on there all the time. And so here is our apparatus that we built. We would fly 16 to 22 telescopes at a time. So every hole you see here is a telescope. Some are big, some are small. And what we needed to do is prove that we don't have any optical aberrations and we're seeing exactly what we expect to see. Because you know what happens when you have a new instrument and you look at the universe in a new way? People will say to you, hey, we know what it's supposed to look like, and it doesn't look the way it's supposed to look based on our understanding of physics, so there's something wrong with your instrument. And that's exactly what people said. But it turns out it wasn't the instrument. It's just that nature throws us surprises. And I'm going to skip that. It's a little complicated. So earlier, I mentioned that I learned to read light. So when I got my first job after getting my PhD, I didn't become a researcher in academia. I became a researcher in Silicon Valley. and I was working on making computer chips. So what you see here is a process chamber where computer chips are made. And what I like to point out to you is that it's glowing. Why is it glowing? Because it's filled with a plasma. Now, when we make computer chips, we use plasmas to either deposit materials in thin layers or to remove materials. But the idea here is that by looking at the plasma light, we should be able to figure out what's happening inside that process chamber. No one had done that before in the way that I'm about to describe. So when I did it for the first time at the turn of the century, it resulted in a set of patents for me. So here's what you see here. This colorful plot you see here in the top left hand is a spectrum versus time. So the x-axis has wavelengths. The colors are how bright the light is, and the y-axis is time. So if I were to take a slice at any time, I would get something that you see here in the bottom right corner. So you see those set of peaks? That's that set of bright lines up there. And so what I did is we can take each one of those lines, which I list here as a spectral band, and look at what is the effect of changing the process on the light. And then I can take a table like this and use AI or my own brain and come up with relations that relate something that's easy to measure, basically spectral lines, and get out something that's difficult to measure, or it would be destructive to measure it. So whenever you are a scientist and you're looking for a new discovery, if you plot your data and you get a straight line out, that's what Henrietta Leavitt got when she studied Cepheid variable stars and discovered the period luminosity relation, which allowed us to make measurements to the distances of galaxies and realize that we live in a universe of galaxies. Hubble used her period luminosity straight line relation to discover his straight line Hubble law, which characterizes the expansion of the universe. For me, it resulted in some patents. For the company, it resulted in millions of dollars. I also like to work on advancing new technologies. So the slide I skipped earlier was a new technology for understanding the sun. And more recently, I worked on a new technology for understanding the expanding universe. So what we see here is what is known as a Hubble diagram. And so what you see is redshift versus distance. But remember, redshift is an indication of the size of the universe versus time. How do I mean that? When light travels through intergalactic space, the light's wavelength gets stretched out by the exact same amount that space expanded while the light was traveling through it. So redshift tells you how much the universe has expanded since the light left that object. Distance is a measurement of time, right? I can say I live a certain number of miles from Washington, D.C., or I can say I live 30 minutes from D.C., and we assume I'm driving at the speed limit. Well, light has a speed limit that we call the speed of light, or the speed of causality. So by plotting redshift versus distance, in a way, you're plotting size of the universe versus time. And what we expected was that the size of the universe would, as the universe is expanding, the expansion would slow down versus time. But instead, we found that for half the age of the universe, it slowed down. But for the other half of the universe, the most recent half, it has been speeding up. The expansion rate of the universe has been accelerating. And that tells us about dark energy. So I worked on this project known as a supernova acceleration probe satellite. And it's gone through many revisions, got combined with another idea, and is now the Nancy Grace Roman telescope. But what I did is I worked on detectors that would allow us to study the high redshift universe. And now those detectors, if you look at previous cameras that were large, that were operational for large telescopes, what you see here is that the detectors that detected the light had gaps between them, right? You couldn't tile them completely. On the one to the left, it's almost tiled completely, but you see those white lines because you have to have a mechanical interface and an electrical interface. For the XMM Newton telescope, what they did is they offset them in 3D. So I worked on creating the first, what we call four-side abuttable packaging for detectors. And I did it. Here's what they look like, my designs. And these went into this new detector that went into the dark energy camera, which started taking data from Chile a bit ago, almost a decade ago. And we also have now the Vera Rubin telescope with the LSST survey that I have, I worked on that as well. This is the largest camera ever built. All the detectors are four-side abutted. No space is wasted. This thing is huge. It's expensive, and I played a tiny role in developing it. I collaborated with the scientists at Brookhaven National Lab. My students and I went there. We worked out the criteria for measuring each of these detectors, because a huge challenge is this thing gets made very cold, and when it does, things warp. Right? So we had to make sure that the focal plane stayed flat to within 10 microns. What's 10 microns? Well, take a millimeter and divide it into 100 parts. One of those is 10 microns, one of those parts. And that's how much these detectors are allowed to warp. Now, the other thing that I did is I decided about a decade ago to start working in a new area. Big data analytics, understanding galaxy formation and evolution, and also understanding the dark sector. And by the dark sector, I mean dark matter and dark energy. What are they? We don't know, but we can place some constraints by observing the matter in our normal universe, in our sector. So here is the Vera Rubin telescope. And so we have these detailed models of how our galaxies are born and how they evolve. And what plays a major role is a process known as accretion. What is accretion? Accretion is to grow via collisions. So our model of galaxy birth is that, there were these competing models. Does a large cloud of gas collapse gravitationally and form stars, or do smaller things come together? And we call that hierarchical galaxy formation. The answer seems to be a combination of both, but the hierarchical galaxy formation is the dominant process. So we expect that we should see hundreds of satellite galaxies and tidal streams surrounding our Milky Way galaxy. So how many have we seen? At the turn of the century, we knew of 3. Nowadays, we know of a few dozen. We're still short by, a factor of 10 almost in how many we should see. So I decided to start doing this study of understanding how our galaxy got to be the way it is today. So each red dot that you see is a detected and observed satellite galaxy of the Milky Way. So formation histories tell you something about universe history, about how the universe evolved. And we can look at the difference in the chemical composition inside our halo, the region surrounding our galaxy, and that can constrain models. And so if you look at a particular type of object that orbits our galaxy and pretty much every other, there are these things called globular clusters. Here's an image of one. Imagine 1 million stars packed into a region of about 100 light years. If you lived on a planet orbiting a star in one of these, your night would be as bright as your day almost, right? And I imagine, what if you're in on an edge of a globular cluster over your galaxy? Then half the year you'd be looking into the globular cluster, and the other half you'd be looking at the face of your galaxy, which would be utterly amazing. So here are the 119 globular clusters that orbit the Milky Way. And what we see is that there are these pulsating stars in them. These we call RR Lyrae stars. Observing these stars and mapping out the 3D distribution of globular clusters in the early 20th century is how Harlow Shapley discovered and measured the size of the Milky Way galaxy and where the Earth is inside the Milky Way galaxy. We thought before his work that the sun was at the center of the galaxy, but now we know different. But we can also use these globular clusters, these pulsating stars, to find new dwarf galaxies. So when they brighten and fade, they do so in a very repeatable manner, and their brightness changes like this little plot you see down here, and they do it over and over. And so because they have a signature for how they brighten and fade, we know, hey, I'm looking at that type of star. And if I know that I'm looking at that type of star, I know how bright they are intrinsically, and then we can calibrate their brightness to within 5%. This means by looking at how bright they appear to be, we can tell how far away they are, because as objects get more distant, they appear less bright. And so here is a study I did with Branimir Cesar. I was not the lead. I was a small part of it. Branimir led it, did the vast majority of the work. But one thing that we did is we found new substructures and maybe even the tidal tails of globular clusters, which had not been seen before. So another thing that I worked on is another star-inspired technology we call MARIA, Magnetic Reconnection Ion Acceleration. So if you look at the pole of the sun, you see that there are these jets that fly off, and they fly off at 3,000 kilometers per second. Our best ion propulsion technologies accelerate ions to 50 to 60 kilometers per second. So the sun is able to accelerate ions to 50 times the speed. And if you accelerate ions out the back of your rocket, if you double the speed of the ions you kick out, you double the force that they apply on your rocket, what you call the thrust. And so you get to go faster more cheaply. So my student, David Chesney, came to me. I was always told my students, look, we're looking at two things. One thing we call scale invariant physics. This means that the same physics occur on various scales. Look for that. It is an opportunity. The other thing I tell my students is pay attention to areas of research that are similar to ours, but is not ours. So that's what my student did. We identified this process that takes place on the scale of millions of miles on the surfaces of stars, on the scales of light years in the cores of galaxies, and on the scales of miles in the magnetospheres of planets. And this is known science, right? You have a configuration that leads to this thing called a fan and a spine. So it happens naturally on the surface of the sun, right? At these little jets that go up. And so you can create one just by having two magnetic poles, right? Like two magnets, a plus minus here, a plus minus there. The magnetic fields will arrange themselves so that you have zero magnetic field along the spine. And then at the fan, they will either all point in or point out. And the they I am referring to is magnetic fields. And so here is a 3D configuration of this magnetic field. So here's the thing. If you want to create this in a lab, you must recreate this magnetic field configuration, and then you have to squeeze it to make it reconnect and get out these 3,000 kilometer per second jets. So what you see here is on the left-hand panel is the squeezing field. There are two magnetic fields. One is a 3D fan spine magnetic configuration, and the third, we call that a perturbation, right? That perturbs that field, squeezes it, and in the right-hand panel, you see the jets form as the perturbation squeezes down, right? So my colleagues and I worked in the lab to actually produce, so there's two questions. How do you create that static 3D field, and how do you create that perturbing field? So using various coils, currents create magnetic fields. Here you go. These are different variations. You know, this is engineering, right? Looking at the sun, inspiring the engineering. And here is a technology that was invented by the people interested in fusion. It's called a dense plasma focus. And it turns out that it produces exactly the type of perturbing field that we need to make our fan spine field reconnect and get out our jets. Here's a model of it. Here's what we did. And here is a video from the lab. So it actually works. And now the last thing I want to talk about is human lives. When I say hacking the stars, I want everybody to be successful. I want to work with the students at George Mason and the students around the country and the students around the world, because education is a pathway to a better life, and a STEM education is almost a sure pathway to a better life. So one of the things I do is I work with various non-governmental organizations, scientific organizations, and the U.S. government. I work with the Department of State, going around the world to help other nations develop their science education, their space science. There I am in Africa. I had in Tanzania, I had a broken hand from playing basketball. They undercut me because I was dominating. You know how it is. Yeah, we were out there playing basketball. This guy, Mark Ginsburg, undercut me. I put my hand down to break my fall and it broke my hand. But no, not that Mark Ginsburg. But here we are. And if you look at the young lady there with the globe under her arm, her name is Susan Marabana, and she was working as a programmer and an accountant at her firm in Nairobi. And she told me in 2006, Hakeem, I really love astronomy thing. Take me under your wing. And I did, and I connected her with the world, and Susan has become an international star in astronomy. Her and her husband, I introduced the two of them, have this project known as the Traveling Telescope, and they have created so many scholars, people from simple communities. Here we are in 2006, where we were going to see the total solar eclipse from Ghana. The gentleman in yellow is my NASA colleague, Alphonse Sterling. He and I are in a documentary created by Dr. Jarita Holbrook called Black Suns, an Astrophysics Adventure. Here are other of my students. The lady in the green dress, the green sweater there, her name is Samaya Fareed. She was an undergraduate. No, she was a master's student when I took her there. She had worked for me 4 years previously as an undergraduate. And then I moved to where she lived, her state of Alabama, to be a professor and work at NASA. And I ran into her in a parking lot. And I said, "Hey, what are you doing now, Samaya?" She had graduated with her bachelor's in physics. And I thought that I was going to hear something amazing. Turns out life had gotten in the way, and she was doing a regular job doing retail. And I said, "Listen, Samaya, no way. You have the it factor. I want you to sign up at my university, and you're going to be my graduate student." And we were there getting her thesis data. Well, today she is Dr. Samaya Fareed at Yale. And the other young lady, Jessica Williamson there, she's been a successful Boeing engineer her entire time. She was an undergraduate at the time. And the guy there in red is my Dave Chesney man and Bryce Orange. The two of them, they formed a company now, and they're doing amazing things in the Caribbean. Bryce runs the observatory at the University of Virgin Islands. They formed a company, and they are commercializing our technology, and everything is looking good as we go. And here I am working on behalf of the Kellogg Foundation to help and make astrophysicists in South Africa. The people you see there are young students from universities around South Africa, and they've all come to the South African Astronomical Observatory, where we teach them winter school. And here I am doing outreach on behalf of the government of the Netherlands. They have a thing called SEEDS, which I forget what it stands for, in Cape Flats. And here I am for the State Department in Algeria, and also in Indonesia, which was the fall of 2019, just before COVID hit. And, for me, it's all about, we use that phrase, paying it forward. But listen, I see us as humanity as having so much capability, but we have to be educated to take advantage of it. And we have to work together, bringing people together and making it happen. That's what I love to do. And you never know what happens when you help people. And so I want to leave with this last video, because when this happened to me in my life, I thought, okay, I've done it all now. I can leave the planet. Aliens abduct me. So here we go.
Launch command issued and liftoff. Mark Vande Hi, Alexander Mazurkin and Joe Acaba lifting off and now on their way to the International Space Station.
I'm NASA astronaut Mark Vande Hei on the International Space Station orbiting 250 miles above our planet. And it's great to be a part of American Graduate Day. I've been fortunate to have had great mentors in my life during both my Army and academic careers. In fact, while at Stanford University studying for a master's in applied physics, one of the people who helped me along the way was Dr. Hakeem Olusay. Hello, Hakeem.
Houston Station on Space to Ground 3.
NASA is a wondrous blend of science, engineering, technology, with mentors at every step of the way. So become a mentor, just like Hakeem was for me. Whoa, help me.
All right. Thank you guys so much for coming out tonight. I love doing science. I love working with students. I love educating, but most of all, I absolutely love impacting lives. And that's what we do here at Mason. So thank you for joining us this evening. And if you have any questions, I'll be very happy to answer all of them. Thank you.
Well, thanks, Hakeem. We've got many questions, actually, and a number of things to talk about. You know, you started your talk this evening and you said right at the outset that the galaxy and the stars, they're light years apart. And you said, you used the word mind-blowing. Well, I have to tell you, my friend, your talk for me was mind-blowing because I've been just thinking about how to wrap my arms around these distances and all of what the galaxy represents. So let me start with a question that's been on my mind, and it's about looking to the future and how we can see the future. I wonder if you can talk a little bit about what the newly launched Webb telescope will bring, the kinds of opportunities it present, the kinds of things we might discover, and just some of your thoughts about what this advance in galactic technology is going to mean for your field and our universe.
Yeah, what has happened in my lifespan and studying the universe has been amazing. And every time we roll out new technologies, now my particle physicists, might disagree, but we see something we did not expect. And that is where the beauty is. So what can we expect from the James Webb Space Telescope? Well, the James Webb Space Telescope is going to have its own missions, but also works in concert with other observatories around the world and in space. So one that I'm so excited about, one partnership is with the TESS satellite, the Transiting Exoplanet Survey Satellite. And I know we have at least one faculty member, Dr. Peter Plavchan, who works in exoplanets. And so what is everybody excited about finding, right? What are we on the cusp of? Finding life on another world, either in our own solar system or on an exoplanet. So we have TESS finding planets around the nearest and brightest stars. And then we have the James Webb Space Telescope that can turn and get a spectrum of those atmospheres of those planets that are orbiting those stars. And perhaps we can find biomarkers of life. Now, the thing about the James Webb Space Telescope also is that it's tuned to the infrared. It's going to look somewhere we've never seen before because, number one, we just didn't have a telescope big enough, and we didn't have a telescope both big enough and tuned to the right wavelengths. But what one thing Webb is designed to do is to identify the first stars and the first galaxies. So when our universe starts, it starts off in what we call the primordial fireball, right? Because it's so hot, atoms cannot exist. Everywhere the universe is filled with a hot, dense plasma, and so the light is interacting very strongly with it, and atoms can't form. But about 380,000 years after the universe began, atoms could form. And once they did, the universe went dark. And we call that era the Dark Ages. Our theorists have been using their equations in physics to understand the Dark Ages, but we've never been able to observe that time in the universe's history and see the first stars come to ignition that we call type 3 stars. We've never seen them, or the first galaxy. So that's really exciting. And one last thing is, well, two, we can observe now the outer reaches of our solar system with both the Rubin telescope and the James Webb telescope. As well, we can look in the dust clouds where stars and planetary systems are being formed. Just like red light penetrates us at sunset. So when you look at the sun at sunset, it appears red. The reason why is because the light is traveling through the atmosphere, the greatest distance it ever will, right? At sunset, the most shallow angle. But what happens is, as the light is traveling through the atmosphere, the blue light gets scattered out in every direction, but the red light makes it straight through. Well, infrared light does the exact same thing. And that's why Webb will be able to look through gas and dust to see where stars and planets are forming. And that's also incredibly exciting.
That's really fascinating. It sounds like the Webb telescope is just going to be a game changer for our
Absolutely.
You know, let me ask a question. We've received a lot of questions over Twitter and on the email account that I mentioned earlier, and some of the themes of questions relates to life in the universe. And there are two questions about life in the universe, and they're two very different but somewhat related things. One of course, and Hakeem, you as an astrophysicist are probably asked this all the time about life on other planets. But we've also received some questions, and I want to ask you about that specifically, your thoughts about life in the galaxy.
Yeah.
Others have asked the questions about colonizing other planets. And planets. So let me ask you about both. Life forms on planets, and our life form going and living and colonizing other planets. What are some of your thoughts?
Absolutely. So earlier this summer, I actually published in May, I think it was, I published an op-ed in the Washington Post on exactly that topic. And then I spent the summer going on various programs discussing the UAP report, the Pentagon UAP report. Now, that was surprising because, you know, I'm being a normal scientist, bringing scientific rigor. And after people watching me on TV, you know what they said? Oh, that dude's a plant from the CIA. He's covering it up. I'm like, no, I'm just being a honest scientist. So life in the universe is, I think it's everywhere. Okay, here's why. As early as we could possibly find evidence of life on Earth, we see it, right? Earth has plate tectonics, and so our surface gets recycled. So even though the planet is 4.5 billion years old, we find clear evidence of life at 3.8 billion. And then if you go 4.2 billion, there are carbon isotopic ratios inside these zircon crystals, which also indicate biology. So that says to me that life gets started really quickly when you have the right conditions. So what are the right conditions? Number one, you need the right atoms to exist. So first generation stars, right? They didn't have planets because the universe is all hydrogen and helium, and you can't make a planet out of hydrogen and helium. Then you get to the second generation of stars. You have some heavier material now. You have heavier atoms. Our sun is a third generation star, and clearly you have enough stuff. So now you have the atoms, but then you need liquids. If you have liquids, then chances are you have everything else, radiation shielding, right temperature, that sort of thing. And then you also need a thermal gradient, because what is life? Life is stable, but it also splits apart, right? What we call reproduction. So what makes things stick together and break apart? Temperature. When it gets cold, things stick together. When it gets warm, they break apart, right? So here's what makes Earth different, though. Earth has a transparent atmosphere. When we look around at planetary bodies, we see that atmospheres, for the most part, come in two types: super thick or non-existent. Mars's atmosphere is virtually non-existent, right? Radiation penetrates a meter or two into the ground at Mars. Titan, Venus, their atmospheres are super thick. If you lived on Titan or Venus, you wouldn't even know that stars exist. Then we have, bigger planets, the ice giants, the gas giants. But Earth is so special because it has this super thin, transparent atmosphere that is protected by a super strong magnetic field. Why? Because the planet is sufficiently big to have a molten part of its core, and it spins sufficiently fast to generate that magnetic field. So Venus doesn't have one, but Earth does. Now here's what you do. You have a big bowl of water. We call it the ocean. You sprinkle some early life in it that is, gets started in the absence of light and in the absence of oxygen. Right? What life needs today, That's not what it needs when it gets started. That stuff is bad for it. But when you shine light on it for billions of years, eventually it says, hey, that's an energy source, and it learns how to do photosynthesis. But when it does photosynthesis, it produces this poison that we call oxygen. So if you look in the geological history of Earth, you can see that every time geological life started producing oxygen through photosynthesis, it killed off life. But just like we create antibiotic-resistant bacteria today by exposing it to antibiotics, life eventually created oxygen-resistant life. And that oxygen-resistant life eventually realized, not, rationally, of course, hey, this oxygen chemistry is much more energetic than this hydrogen sulfide chemistry, and so we can now support multicellular beings like ourselves. That took 4 billion years. Then we have the Ediacaran period and the Cambrian explosion, and then we get to ourselves. So if you get multicellular life, what's the probability of getting intelligence? I think it's a virtual certainty. But I also don't consider humans to be the only intelligent life forms on the Earth. Humans are the only technologically advanced intelligent life form on Earth. Now, being technologically advanced, again, super rare, right? So Earth has these two bottlenecks. We made it past the light oxygen bottleneck to get to multicellularity. And then one species out of the how many that have existed developed high technology. That is extremely rare. So if you ask me, I would guess that life exists in our solar system, elsewhere where there are liquids, and where it's protected essentially, but there's not technological life in our solar system. Does it exist in our galaxy? We exist, so sure, it exists in the universe. So we know it exists. Maybe it is, but I think we're early. I think later in the history of the universe, you'll get more and more planets with life and with technologically advanced life, but we are effectively alone because space is just so darn big. So now, the idea of colonizing other planets. So, we're in a time now where everybody counts, everybody speaks their truth, and there's a lot of people that just don't like that word colonizing, right? So when you say colonizing other planets, that triggers people, right? I'm not one of those people. I understand what you mean. What do you think about humans visiting other planets? I think that's a great idea. Just because we're explorers, right? It's like when humans left Africa and went out to Eurasia and then spread around the world. Let's spread around the galaxy. Let's just do it. Now, mind you, sometimes we'll say, oh, the sun is going to go red giant. But look, we got about 1 billion years before the sun is unlivable. Earth is unlivable for us. So what does that mean? We have about 1.5 billion year window for civilization to come into existence and do its thing. And let me not even get into fossil fuels, how lucky we are to have that. The fact that the bacteria and the fungi that would decay the plants in the ocean and on land did not exist. So that stuff just built up over billions of years and eventually became our fossil fuel. So we have this other super energetic source, right? What is it? Life that's been concentrated. We make biofuels. Life is concentrated energy, right? So let's spread out. Let's explore for the sake of exploration. Because even if Earth got hit by a giant meteor tomorrow, it will still be better than anywhere else in the universe for us, right? So we have to take care of our home. It's not like, let's abandon Earth and move to a new planet. It's like, let's just spread out and explore.
Well, thanks. A very interesting conversation. and certainly I think many people who think about the galaxy, people who think about looking up at the stars, that's one of the first things they think about is what's out there and what if I could get there. So very interesting. We have time for a couple of more questions. I want to ask you, one that came through one of the Twitter accounts. That's a very interesting one too. You talked a lot about the sun and about the acceleration of particles out of the sun, and a thoughtful question came in about, in your view, what role the sun has played in climate change and the climate changes we see on our planet today. Is that a factor? And what's your perspective on that?
Yeah. So you know what? Even better to say is, what effect does our space environment have on our own climate? So one of the earliest studies that showed a correlation was by some of my colleagues at Lawrence Berkeley Laboratory, Rich Muller et al. So Rich Muller was a friend of Louis Alvarez and Louis Alvarez Jr., who discovered the KT boundary layer, and showed that, the dinosaurs were killed off likely by a huge collision, plus all these darn volcanoes over there, right? So another thing that he did is he studied ice cores and looked at Earth's temperature over time, and found that there was a periodicity. We're mostly cold with these periodic warm periods, and we're in an extended warm period. But the crazy thing about that was that the period matched another period. And what is that other period? Well, if you look at our solar system, as it orbits the galaxy, it's sort of like tilted on its side, orbiting around the galaxy, but it also bobs up and down in and out of the plane of the galaxy. And it turns out that the period of Earth's climate variations match the period of Earth bobbing up and down in and out of the plane of the galaxy. So are the two correlated? We don't know. Another thing that we had was the Maunder minimum, where there was a time period where the sun had many fewer sunspots, and Europe went into its little ice age at that time. We cannot conclusively say that one led to the other. And that's the problem with weather predicting, right? Is that when you look at, the sun forcing, the oceans storing heat, the currents in the ocean, and how the heat is distributed, there are so many effects that impact our climate that is hard to nail down. When you're looking at the gaseous composition of the atmosphere, that's sort of the easy thing to do, right? It's going to get hotter or get cooler because of the gaseous composition and how it interacts with the light, right? Either it traps more infrared or lets it go. But it is a butterfly effect type problem, and I don't know the answer. We've seen correlations, but we also see anti-correlations. For example, the sun is getting brighter and brighter and brighter, right? As it grows, it gets bigger as it ages, and it grows. So the sun, and not only that, in the geological record, we see that the variation in the solar output varied much more than it does right now, but we also don't see correlated climate effects with those changes. So, it's not clear to me. If something came out, I haven't read about this stuff in a couple of years, so, we'll see. I'll read more. Read the latest papers. Yeah.
Interesting. Thanks for that response. So soon after you joined Mason, I remember turning on the TV one day, and it was the day that one of the more commercial new space flights are coming up, and you were commentators, I think, on one of the national networks on the launch. Yeah. And so I couldn't help but ask a question, because someone else mentioned it as well, is what some of your thoughts are about the commercialization of space flights. And of course, even driving into the university this morning, I heard about the challenges of space junk and how catastrophic that could be. But in general, I guess I'm wondering about your thoughts as the various corporations now are involved in the commercialization of our adventures in space.
Right. So what we're seeing here is what I consider to be a natural evolution. We've been aspirational in our space vision as Americans. And, we've gotten to a place that many thought maybe we would never get to. I remember in the 90s, talking about the commercialization of space. So the thing about the so-called billionaire space race that we just went through is that those cats have brought down the price of access to space significantly. And so by doing so, they create a new infrastructure, which creates a new opportunity, right? Now, having access to space means greater access to space means our students can access space. Now, one of the things that we do to deal with the space junk problem is that after a certain time, if you put something in space, according to treaties and law, you have to have a plan for deorbiting it. Right. So, but, nations do go rogue from time to time and do things like shoot down their own satellite, creating a lot of debris in space. In general, creating this new infrastructure of low cost access to space, I think, is a good thing. How will it play out? Well, could you have predicted how the internet would play out? Cars, these new technologies. But what they do create is new opportunity. And, one of the things about Earth and humans is we always need resources. We get them out of the Earth, but there are certain things that are just floating around in space. Like there was this one asteroid that's worth like trillions, of dollars out there, and NASA actually has a mission to that particular asteroid called Psyche to evaluate it. So that's one, economic opportunity, but scientific opportunities, the most important object that we observe from space is the Earth, right? And so maintaining the Earth, whether it's water, crops, forests, glaciers, we do that through space. And so to the degree, and also you see Starlink satellites, to the chagrin of the astronomy community, are trying to get over the digital divide and bring access to the internet to the world using small satellites. So there's so much opportunity. I think it's a good thing.
Great. Let's finish with a personal question that somebody asked. I think it's a really good one, because I think not only is the question interesting, but I think your response could be really very motivating for others. And the question essentially is something like this, particularly coming from a background where, as you said earlier, education was not the most valuable part of your socialization as a young child, but you were motivated to go to college. You eventually got your PhD, which is impressive in its own right for anybody who's gone through that process, as we both have. We know how and how persistent you need to be. But the question wasn't about that. It was both what motivated you to go into the PhD level, but in such a dramatic and complex field as the one you did. And what motivated you personally to become the professional in the field that you are today, the internationally renowned physicist that you are?
That's a tough question, because you know how it is, right? You're doing your work every day, and then you look up one day and people are, I remember, I used to go to this one conference every year, the National Society of Black Physicists. By the way, I'm now the president, okay? Newly elected president. I take over March 1st as president officially. But, I would go to that conference every year to get motivated, to talk to mentors. And then one year I show up and young people are coming up to me asking me questions. And I'm like, when did this happen? I still see myself as that curious kid, right? And so I had curiosity, but I also had a desire to live indoors and eat, And, I went to the military right out of high school. And I ended up leaving the Navy, it was sort of by choice, but I have atopic dermatitis, and, you're not allowed in the Navy with it. And it disqualified me for what I went there for. So I was allowed to either leave or stay and, chip paint. So every step of the way, I was discovering myself, right? So I was curious about the world. I studied Albert Einstein for like a decade before I stepped foot into a university. And I did not know that I was preparing myself to do physics. So whereas the other people, someone said physics is complicated, for me, physics was the one major that was easy. Now, the other thing about, success is identity. If you see yourself a certain way, that either can help push you up or pull you down. And so, I saw myself not as the scholar. I saw myself closer to like the gangster. So I never went to class, Mark, And so in physics, I went to math classes because I was very badly educated in math, and I knew I had to know math to do physics. But for physics, I could just show up to the exams, and my exam was the key, right? And so it started off being, I love Albert Einstein. I love nature. So this is a key thing. People say you love science. I always correct them. I'm like, no, science is hard. I love nature. Doing science is a rigorous process, and I do love it. And I love working with the people, but it's really nature that's the inspiring thing, right? And so for me, I had not a natural knack. I practiced logic problems all through my childhood. And so doing physics was like doing logic problems. So for me, physics is what was easy, and it's also what was inspiring to me, right? So it was almost as if I had to do it. It was calling me. It was saying, hey man, this is you. You do this, right? And don't get me wrong, as the world's greatest basketball player in the history of basketball, maybe I should have done that. Okay, that was a joke. I always got to throw it out there because I'm competitive. Okay, I'm probably not in the top 1,000 people on George Mason campus at this point, but
Let me ask you, we have time. We have about 60 seconds left. So,
Yes, sir.
I'll be brief, and that's good. But I want to ask you this. When you go outside of your house, and I know you're at your home, when you walk outside of your house and you look up at the stars, what is it that you see?
I see the sky in 3D. And that, the first time it happened, blew my mind. We come full circle. So let me just give you an example of what I mean by that. When you look at the night sky and you see the moon and you're looking past it to Venus, and you know where the Venus is relative to the sun. And if you're sufficiently nerdy, you know where Jupiter and Saturn are, and you see them, if you know their relative sizes and you know their relative distances, you can see it in 3D. Now get this, you know how something looks smaller the farther away it is? Our nearest large galaxy, the Andromeda Galaxy, is 2 million light years away. So how big would you imagine that appears in our sky? A tiny speck? Yeah, no, it's 6 times bigger than a full moon. So imagine if you know the size of that thing, you know the distance of that thing to it, and you see its size, and that really can blow your mind in a way that just, you have to feel it to believe it, right? Now, there's another thing. Here we're looking at the northern hemisphere sky. When I go to the southern hemisphere, where the center of the galaxy is directly overhead, and you can actually see star clusters and nebulae, and you can also see our satellite galaxies. Oh man, now you're seeing 3D in another way, right? You see yourself inside this galaxy and looking out at the vista, right? Is how you can imagine. Right? It's like Earth is a hill at which we're looking out at the vista of the galaxy laid out before us. It's profound.
Well, Hakeem Al-Shehi, thank you so much. Visiting Robinson Professor at George Mason University. Thank you for informing us, but more importantly, thank you this evening for inspiring us.
Thank you, sir.
Started your talk about having blown your mind. I think you accomplished that feat tonight, because I think your conversation opened our minds to some places where it's really exciting and inspiring to go. Thank you so much. Thank you for joining us this evening for the Mason Vision series. All of you who are participating with us online or in other ways. And if you're watching the recording of this, thank you for watching it as well. And look for future Mason Vision series programs. We'll have one in March and one in April. I look forward to having you join us. And again, Hakeem, thank you so much for informing and inspiring and participating in the Mason Vision series. Thanks to all. Good night. Be safe. Thanks very much. Good evening, everybody.